Hello and welcome back to another Algebra 1 lesson. We're going to look at descriptive modeling and accuracy today. So let's jump right into our lesson. We're going to do the warm-up. As always, pause the video and take a minute to read and answer these questions. So you're measuring the amount of flour to add. Obviously, we're going to use a cup. You do not want to add a gallon of flour. And if you're making cookie dough, a teaspoon is not going to be quite enough. So we're going to use 1 cup measuring. Okay, if we're talking about the circumference of a softball's not huge. We're not going to want to use a foot. 1/8 of an inch is way too small, so we want to use an inch. Travel time from one side of your city to the other by car, we're going to use minutes, especially if you're talking about Portsmouth. If you're talking about a huge city like New York City, you might maybe want to use hours, but for Portsmouth, you would want to use minutes. And you're estimating the time to travel from Washington, D.C. to Orlando, Florida by car, and that's going to take hours. All right, I don't know why this is dragging all around. It won't stop. Okay, there we go. Next resource. So let's look at today's standards. Today's standards are in Q2 and Q3. What we're wanting to do is look at appropriate quantities for the purpose of descriptive modeling. Choose the level of accuracy that is appropriate to limitations on measurements when reporting quantities. So key vocabulary. There's a few words here that you might want to write down or make sure that you're highlighting if you're following along in your student workbook. But descriptive modeling is a way to mathematically describe real-world situations and the factors that cause them. And that's what we're really going to be talking about. And then we have a metric, which is just a rule for assigning a number to some characteristic or attribute. And accuracy is how near we are to the actual measurement. So let's jump in with the learn. Descriptive modeling is a way to mathematically describe real-world situations and the factors that cause them. Once again, this metric is a rule for assigning a number to some characteristics or attributes. Metrics can be used to make comparisons. In sports, earned run average is used to compare baseball pitchers, and the quarterback rating compares the performance of football quarterbacks. In banking, a person's debt-to-income ratio can determine whether they qualify for a loan or not. In a good metric, factors that are important in the situation are considered and included in the metric. For example, the quarterback rating includes measures of passing, running, penalties, and other factors that would make a quarterback effective. So looking at example 1, we're on page 49 in your student workbook if you're following along. It says that some universities use a metric called the academic index to qualify high school athletic recruits. Use the expression to determine whether the student athlete qualifies at a university that requires an academic index of 186 or greater. Okay, so what it tells me to do is take their reading and writing scores, add those together, divide by 2, add their math score, then divide it by 20, then times that entire quantity by 2, then add in their GPA value. So we're going to have to fill in the blanks here and kind of see. We know their GPA is 3.1. So if I look down here at a GPA of 3.1, the GPA value, which is what this asks for, is 68. So in place of this GPA value, we're going to want to plug in 68. Their reading score and their writing score. Reading is 610, writing is 640. We're going to add those together, then divide by 2. Then add that to their math score of 700. So step 1 is to find the values for the metric. We just discussed that. The 3.1 GPA has a value of 68. Substitute the values into the metric, the 610, the 640, the 700, and that's 68. And then we can calculate. So we end up with a 200.5. If we look back up at the original question, it said it requires an academic of index of 186 or greater. So since we have a 200.5, we realize that their academic index does meet the criteria. It's greater than 186, therefore our student does qualify for this university. All right, following along, example 2, compare metrics. So if I'm comparing metrics, we're looking at height. A child's adult height can be predicted using several metrics. Given the height of the mother, the father, and their son at 2 years old, let's use the metrics to predict the son's height as an adult. I remember somebody telling me this, that what my son's height was at 2 years old, if I was to double it, that would be his height at age, I think they said 18 or 21. I don't know, maybe as an adult. But I remember calculating it and thinking, all right, he's going to be 6 foot. So the Gray method uses the average heights of parents adjusted by the gender of the child. So for a boy, the mother's height is multiplied by 13/12, and for a girl, the father's height is multiplied by 12/13. I don't know who comes up with this stuff, but it's kind of cool. So we take the mother's height, which is 65 inches, and since this is a boy, we're going to multiply it by 13/12. So 13/12 times her height of 65 plus the father's height, which is 72. We add that by, or divide that by 2 after we've added them together to find the average. And we get 71.21 as the child's height, what the boy's supposed to be as an adult. He's supposed to be about 71 inches tall. Okay, so that's the Gray method. So let's look at the other method, the doubling method. This is the one that I did. The doubling method multiplies the height of a child by 2 at the age of 2 by a specific, let me start over. The doubling method multiplies the height of a child by 2 at a specific age to predict the child's height as an adult. So height at 24 months is used for boys and height at 18 months is used for girls. So 2 times 35 gives us a height of 70. So notice that they're pretty similar. The other one was 71 inches, I believe. Yes, and this one is 70 inches. Pretty interesting that both methods are so close. So this is just comparing metrics. This is comparing ways that we make estimations on a child's height as an adult based on their height and their parents' height when they're 2 years old. So the important thing to think about when we're making these predictions and using metrics and things is how accurate is this? All measurements are approximations. When you measure something, you're limited by the measurement tool that you're using. Accuracy is the nearness of a measurement to the true value of the measure. So consider the timer shown. The accuracy needed for baking cookies, timing the final seconds of a basketball game, and determining the gold medalist of a 100-meter dash are all very different. So when we are thinking about this, some things to consider, like if I'm talking about time, we can only use to the nearest second by looking at a clock because the clock only tells time in hours, minutes, and seconds. So I cannot go to 100th of a second just by looking at a regular clock. I'm looking at the one in my classroom because it only has a second hand. It doesn't have 100th of a second hand. So the closest that I can be on my accuracy of their time is to the nearest second. So fractions may be more accurate than rounded decimals. So for example, the sum of 3/7 and 2/3 is more accurately reported as 23/21 than 1.095. So then we have to decide where to round, and that's going to affect our accuracy. So Damien and 2 of his friends were taking a road trip. They planned to share the responsibility of driving and will each drive an equal distance. Damien's GPS shows that the total distance is 172 miles. So let's determine the exact distance that each person should drive. Then determine a more appropriate driving distance for each person given the limitations of the situation. So to determine the exact distance that each person should drive, since there's 3 people driving, we should take the distance and divide it equally among the 3 people. The problem here is that 172 divided by 3 is 57.3 repeating miles. So what is 0.3 repeating miles? Well, because the distance given by the GPS is accurate to the nearest mile, the distance each driver will drive should be rounded to the nearest mile. So each driver will drive approximately 57 miles. We can check our answers. And they are correct. We can't say that they're going to drive 57.3 repeating miles because our tripometer doesn't calculate, or in this case, the GPS system does not do tenths of a mile. It only does to the nearest mile. So we're going to estimate, and each person's going to drive 57 miles. All right, and finding an appropriate level of accuracy. So in 2012, NASA's space shuttle, the Endeavour, traveled approximately 897 miles from Kennedy Space Center to Houston, Texas by a shuttle carrier aircraft. Then it traveled about 1,381 miles to the Los Angeles International Airport. Finally, a truck pulled the Endeavour 12 miles through the streets of Los Angeles to the California Science Center. If the shuttle carrier aircraft flew at an average speed of 287 miles per hour, and the truck drove at an average speed of 1.3 miles per hour, determine the total amount of time it took the Endeavour to travel from the Kennedy Space Center to the California Science Center with a reasonable level of accuracy. So first, let's begin by looking. It traveled 897 miles by a shuttle carrier aircraft. If we look here, it says that the shuttle carrier aircraft flew at an average speed of 287 miles per hour. So we're trying to find out how long it took to get there. So if we go 287 miles per hour, and it went a total of 897 miles, then what we're going to look at, and then another 1,381 miles, we can add those two numbers together, and that's going to give me the total miles that it traveled, so 2,278 miles at a speed of 287 miles per hour. So we're dividing that miles per hour. Then it went an additional 12 miles at a speed of 1.3 miles per hour. So we're going to add to that value the 12 miles it traveled at a speed of 1.3 miles per hour. So if I was to divide this first number, I get 7.937 hours. Dividing the second, I get 9.231 hours. So adding the two together, we get 17.168 hours. Who goes around saying, I traveled 17.16 hours to reach my destination? No one says that. We would round down. We would say, it traveled for approximately 17 hours. So the total travel time for the Endeavour was about 17 hours. Example 5, determining accuracy once again. Looking at the U.S. Census Bureau website, it gives the population of the United States on a certain day. How accurate is the reported population? Do you think that this is exactly how many people there are in the United States on the day that this happened? Probably not, seeing that there's one birth every 7 seconds, one death every 13 seconds, an international migrant every 29 seconds, and a net gain of one person every 11 seconds. That's a lot happening in a day. So if this is giving it on a particular day, we don't know how many births happened that day. We don't know how many deaths happened that day. We don't know how many people legally migrated into the country. We don't know how many people illegally migrated into the country. We have no clue. So there's no way to count every person. We can't set and do a head count at any given moment. Giving an exact population doesn't make any sense. The number of births, deaths, and immigrations varies, so the population does not change at a steady rate. So the website just shows an average. It would be more appropriate for the website to report the population as, what do you think? 300 million, 329.2 million, or 329.158020. I think we can all agree to rule that one out. So should we do 329.2 million or 300 million? It's kind of tricky. I'm assuming that we would want to round as closely as possible without being extremely specific. So this gives us 200 thousandths of a person, like we've got 329,200,000. So that takes into account the deaths, it gives us a little bit of leeway. It's not so specific like this one that there's only 3 people difference. It's not so vague that we're just saying, well, 300 million people. But it rounds to the nearest thousands of people. So that is the best answer for this given problem. All right, and the last thing that I would like for you guys to do today is do this exit ticket. It says Gustavo needs to decide which activities he should participate in after school. He has developed a metric based on the element of each activity and his own interests. Use the metric to calculate a score for each activity to the nearest tenth. So what I would like for you to do is on a piece of paper, complete this exit ticket. Go ahead and do number 1 and number 2. And you're going to submit that online via Google Classroom. I want you to take a picture of your work and upload it there so that I can give you credit for watching the video and for completing the exit ticket. All right, guys, have a great day.